Hey, good morning. Justin here with AeroCore, and today we've got a chance to fly a pretty cool aircraft, this BO-105 helicopter that you see behind me. So I think the biggest claim to fame for this aircraft has got to be the rigid rotor head that's up on top. Now what that does is it really allows this aircraft to achieve a level of maneuverability that most helicopters just can't achieve. So most helicopters, the blades are mounted to the rotor head in some sort of a flexible way. Either with a hinge or an elastomeric bearing or something that allows that blade to move with respect to the rotor system. So it can flap up and down, it can lead fore and aft. Whereas on this helicopter, that movement is all eliminated. It's just rigidly mounted up on there so the blade can't move with respect to the helicopter. And again, what that does is it really removes any limitations that we have in terms of maneuvers. So if we go back here to the back part of the helicopter, normally if you had a blade that was just mounted on a hinge, there's nothing limiting the total travel of that blade. The only restorative force that we have is essentially the centrifugal force of the blades rotating. So in an extreme scenario, you could run into a situation where the blade could flex down to the point where it could contact a tail boom or otherwise have some sort of, let's say, non-optimal outcome. And with this helicopter, we've eliminated that possibility. Any movement of the blade is going to result in a movement of the helicopter, and the motion of those blades is really going to be limited to some extent. So it allows us to achieve really maneuvers that we can't achieve in any other helicopter. So you might be wondering why other helicopters mount their blades in this way. So we have rotor systems that are typically referred to as fully articulated or semi-rigid. And really the reason is that as we fly a helicopter forward into the airflow, there's going to be a dissymmetry that occurs across the rotor disc. So you have one blade that's moving into the oncoming airflow, one blade that's moving out of the oncoming airflow, and as a result, the airspeed that those blades experience is going to be different from one side of the rotor to the other. So you're going to create different levels of lift on one side or the other. So by mounting those blades in a way where they can move, it's naturally going to account for this. So one blade's going to move up into the airflow and reduce the angle of attack. One blade's going to move down with respect to that airflow, increasing the angle of attack, and just naturally compensate for those dissymmetries. With this system, we still have to do that, but all of those activities are taken by the blades themselves. The blades are flexible, so they will bend, they will flap up and down just within the blade, not on a hinge, but just the blade itself will bend or distort to achieve that same outcome. So again, it has a lot more maneuverability, but we would not be able to use a traditional metal blade because you'd run into fatigue limits with those blades. So these are all composite blades. They don't have the same fatigue life limits. You know, again, pretty advanced, pretty cool little system. This helicopter is really way overbuilt. That same rotor head was eventually used on the follow-on product to this aircraft. It was used on the BK-117. That aircraft is about 40% heavier than this aircraft, same rotor head. So again, it just goes to show how overbuilt and how much margin we really have for loading up that rotor head. It's a pretty cool little machine. A lesser talked about, but I think equally notable feature of these aircraft is this was really the first light twin aircraft, so or helicopter rather. So this has the Rolls-Royce M250 engines back here. This particular variant on this helicopter is the C-20B. So same engine that's used in other helicopters like a Bell 206 Jet Ranger uses the same engine. We've got two of them. So a lot more performance, a lot more power on tap with this helicopter. Again, just makes it a joy to fly. Really allows you to do a lot with it. One more interesting note with this particular example, this is a P1M version, came out of the German military. A little bit different than its civilian cousin like a CBS-4 as an example. So the civilian versions, their transmission is limited to a total of 85% torque with all engines running. This particular helicopter, we've got uprated gearboxes. We can pull 100% torque. And really the reason they did that was because these aircraft would typically be carrying heavy loads with ordnance. You wanted to have the extra power available. In the civilian world, even the 85% is a lot more than we ever need. I really don't ever bump up against that limit when we're flying something like a CBS-4 and we're just kind of carrying passengers around. So having the extra power capability to do 100% torque with this aircraft means we're really never worried about over torquing it. So It's pretty easy to fly in that regard. From a pilot workload standpoint, we're not worried about the NG limits, we're not worried about our torque limits. We really just have to watch our TOT limits. It makes it a lot easier to fly. So in any event, enough about the outside of the aircraft, let's check out the inside.
All right, well, welcome aboard the BO-105 today. We thought we'd give you a little bit of a longer introduction to the aircraft and sort of the start sequence. So this particular aircraft that we're flying, it's pretty much a stock aircraft. It's a BO-105 P1M, came out of the German military. So it's been demilitarized, so normally there would be a weapon systems power switch and a yaw control power switch that would be here. That's been removed. A couple other items have been removed, and obviously we've had a civilian GPS and a civilian radio that's been added. But for the most part, a lot of these instruments that you see are pretty stock. So to give you a quick tour around the cockpit, up here we have sort of the Aviate instruments, airspeed, artificial horizon, VSR, BSI, and altimeter. The radio and the GPS we already mentioned. Caution warning panel. All the engine instrumentation here. So we've got our NG, our TOT, our engine oil pressure. These are left and right. Engine oil temperature. And then we've got transmission indications here. So there's two pickups on the transmission for pressure, one for temperature. Up here we've got our torque indication. Kind of an interesting little gauge. So we already mentioned this P1M model has a higher torque limit. You can see it goes all the way up to 100% there. And when you compare this to the gauge that you see in a lot of the civilian models, number one, it's much larger, so it gives you more fidelity to be able to see what torque you're actually demanding for the aircraft. The other thing is, so these gauges, they use oil out of the transmission system as a hydraulic fluid to actually move the needle and determine how much torque you're demanding. And that system is subject to vibration, it's subject to inconsistencies in pressure, so you tend to get little movement in the needle, especially in the civilian version. What they've done with this system in the military one was they've actually reintroduced a small cavity of air right at the end of the system that serves as, air is compressible, so it serves as essentially a shock absorber. So when you get these little variations in the oil pressure, that dampens that out and we get a lot more consistent indication of these gauges. It's a pretty little nifty device. Interestingly enough, we almost don't even need it because, like I say, we're never going to really reach the 100% torque limit as long as we've got both engines running. If we lose an engine and we're down to one engine, then we may reach that limit. But for the most part, even though I love these gauges, you almost don't even need them. Up here we've got our mast moment indicator. So what this is, in terms of physics, a moment, what you're measuring with a moment is a rotational force. So this is connected to the rotor mast, and it's related to that rigid rotor system we were talking about earlier. So what we're measuring is rotational force on the rotor mast, and we're not measuring rotation around the z-axis. We're not measuring yaw of the helicopter. We're measuring pitch and roll, so rotations around the y-axis and the x-axis. So under normal circumstances, if you had a fully articulated rotor system and you were to impart any sort of a pitch motion into the helicopter, well, let's back up a second. When you impart pitch motion changes into the rotor disc, that's going to try to move the helicopter. And when we are in the air, normally you move the rotor disc, you move the rotor head, and the helicopter goes with it. So you don't get a whole lot of loads in the system. But when we're on the ground like this, the helicopter can't move. So now the rotor disc starts to move, the helicopter's stationary, and you get a difference in motion between the two of them. And that's what we're accounting for, because in the fully articulated system, the blades are all attached by hinges, so the blades are free to move and relieve that pressure, so you don't get a buildup of forces in the rotor mast. Whereas on the rigid rotor system, those forces can't go anywhere, and so you start to get an actual bending of the rotor mast. You get a moment, a rotation of the rotor mast, either forward or laterally. And so there's a strain gauge that's attached to the rotor mast that's measuring that force in the rotor mast. So it's entirely possible if we're on the ground, we've got the rotor spun up, and we start moving the cyclic around in extreme directions, that we could damage the rotor head. So this is going to monitor that force. And you can see this light that's lit up here that's going to tell us if we've exceeded any of those limits. And if we do, we have to go up, and the first thing we check is the torque on the bolts that attach the rotor head to the mast to see if we've induced any sort of a separation between those two units. And if we have to start looking deeper. But as part of pre-flight, what we'll do is hit this test switch. You can see we get full range of motion. There's a limit indication. You want to make sure that needle goes back to limit indication to tell if it's actually been calibrated correctly, and it will clear that limit notification. So now, if we are flying along or if we're on the ground and this lights back up, we know we actually had a true limit. So, okay, so to go through the rest of the start sequence, first thing we're going to do is test our caution warning panel. We want to just make sure that all of our indications are functional. Little side note, like most things in this helicopter, there is some redundancy built in. All of these indications have a left and a right light bulb inside, so we can even tolerate a small failure. If we had a light bulb burn out, we won't lose the indication. So we can see all of those are working. We can test our fire system, left and right, make sure those lights are working. The next thing we want to check is our hydraulic system. So this helicopter has a dual hydraulic system that boosts the flight controls. So if we were just manually controlling the flight controls with no hydraulic assistance, those loads would be too much for a human to tolerate. So the hydraulic system provides a mechanical boost so that we can actually control the helicopter. So we have a System 1 and System 2. They're always running in parallel with each other. So if we have a blockage of the first system, the system automatically adjusts over or changes over to System number 2. System number 2 takes over, and therefore we have full redundancy. So what we want to test is that changeover mechanism is working. So when the system is off, we're not running the helicopter, the rotors aren't turning. If we move the flight controls, since there's no pressure being applied to any of those flight controls, it's essentially interpreting our motion as being the same thing as a failure of the number 1 hydraulics. So what we should see, if we move the flight controls, is a failure indication here that it's changed over, that slide mechanism has engaged and changed over the active system from number 1 to number 2. So I'll go ahead and push this stick forward, and you can see we get this hide 1 servo light that kicks on that tells us it's now activated system number 2. So what we want to do is test that system in all axes. So there's 3 controls up there. There's pitch, roll, and the collective. So we want to test all of those in both directions. So we've checked stick forward. We'll come down here and go ahead and reset that. It clears the light. We'll check stick aft. We'll reset it again. Stick left, we'll reset it again. To the right, we'll reset it again. And then we'll bump the we'll bump the collective a little bit. And then what we're going to do is just leave that alone. So now the system is utilizing the number 2 hydraulics. So when we fire up the helicopter, we can check that the number 2 hydraulic system is actually functional, change it back to number 1, and conduct our flight on number 1. So that way we've checked both of our hydraulic systems, ensuring those are both functional. Okay. So we're now getting ready to start the engines. We're going to start the number 1 engine first. We're going to start the right engine first. I take that back. So there's several things that we're looking for on an engine start. So accelerating a turbine engine is always a little bit of a dance between bringing the fuel in and managing the temperature. So turbine engines need more fuel to accelerate, but the slower the engine is, the slower it's going to accelerate, and the more heat is going to go into the engine. So you can imagine if it was very, very slow, like maybe 1% power, it would be this long process where you bring in a little bit more fuel, it expands air, it introduces more heat. You have to wait for some of that air to go out the back of the engine, which then turns the turbine, which then turns the compressor, which draws more air in, which brings the temperature back down. So when the engine is slow, that process happens very slowly. So if you were to bring in a lot of fuel quickly, that would raise the temperature to an unacceptable level. When the engine's running fast, up at 97% power, you can bring in a lot of fuel and it will just accelerate quickly, and we won't have that same temperature gain. So some engines have what we call a modulated start, where you can just control that fuel level and you can bring in the fuel as fast or as slow as you want. We don't have a modulated start. We have essentially a binary selection with the fuel, where you either bring in the fuel or you don't bring in the fuel, and then you have a mechanical controller that's preset to introduce fuel at certain levels. So we don't have direct control. We do have sort of indirect control, meaning that We can control when the fuel is brought in, and in some cases we can control the power that we're applying to the starter by either utilizing a strong battery, using the cross-gen start, or utilizing a GPU. So the more power we can put on the starter, the faster it's going to turn that engine, the cooler the start's going to be, because the more acceleration we're getting from the starter. Also, the higher the RPM we can attain from the engine before we engage the fuel, the colder the start's going to be, because the less accelerating the fire and the fuel has to do, and the faster the engine already is. And finally, you can see we've got some temperature in the engine. That's because we were flying earlier today, and we sat down here, and there's still some residual heat in the engine. So one of the things we can also do is just run the starter for a little bit to draw cool air through the engine and cool it down before we try to reignite it. That will also help us with a cooler start. And we do have limits on our starter. So with this particular helicopter, from the time we energize the starter, this is our timer here, from the time we energize the starter until the time we get ignition is a 30-second limit. And that may not sound like a lot, and that a lot of times that induces pilots to sort of be in a rush to get the engine started, but 30 seconds is a lot of time. So you'll see today, we'll energize the starter, we'll wait for the NG, the speed of the engine, to sort of top out as much as it can. We'll allow some air to come through and cool the engine. It'll probably only be about 10 seconds that we'll need to do that before bringing in fuel, so we won't be anywhere close to our starter limits bringing in the engine. Once we've reached our minimum idle speed, we can release the starter. We want to make sure that we've got good oil pressure. We will get a warning from our caution warning panel here that's going to flash RPM. So that's actually a dual warning system that will activate if we have a split in torques, which is really advising us in flight if we had some sort of a power loss or engine failure. And it will also come up again later when we have as a low rotor RPM indication. So if it's the result of a torque split, which this initial start will be, then we can silence it with this button here on the cyclic. So we'll do that during the start. But once we've released the starter, we just want to give the system a little bit of time to recover. So we'll allow the starter to cool. We'll allow the rotor head to start speeding up. Again, we want to monitor all of our pressures, so we'll make sure that we start to get some indications on our transmission oil pressure. I usually wait until about 40% here on our rotor RPM. That's just a good sort of timing mechanism. So once we've spooled up to about 40%, then I'm free to turn on the generator and let our battery start to recover, and then we can start doing some checks. So go ahead and close the door. The one last thing we have to do is turn on these overhead fuel pumps that you see here. We've got 4 fuel pumps. You can see these fuel pump lights are extinguished, and this low fuel light will extinguish shortly, so we have, there it's extinguished. We've got 2 fuel tanks, the main fuel tank and the supply tank. The supply tank feeds directly into the engines. 2 of those pumps are moving fuel from the main tank to the supply tank constantly, and when you sit for a little while, you can get fuel that drains from the supply tank back to the main tank. The low fuel light is connected to that supply tank, so that's why we were sitting here. You saw that low fuel light come on. Then we turn the pumps on, it refills the supply tank and extinguishes that light. The other 2 pumps are supplying positive pressure to the engine. So there's a high pressure engine fuel pump, and then these are low pressure fuel pumps that are actually feeding those pumps to take the stress off of those pumps. So here's our starter mechanism. Right here is our start switch that activates the starter and the ignition sparkers. And then this is our fuel. We'll bring that forward. So you can see as we get ready to start. One more thing we want to do is just check our battery voltage one more time. We've been sitting here with the power applied, just talking on the camera for a second. So we want to make sure we have good battery volts, and that's just a precursor to make sure that we're not going to over-temp an engine. Again, if we don't have a lot of power to put into that starter, then there's going to be more heat that's going to build up as a result of that. So we still have over 25 volts in the battery, so it's a good, powerful battery. When we hit the starter and put a load on the starter, I also come down here and just give one more check to the volts to make sure that we're still putting out good power from the battery. So we'll go ahead and engage the starter. We'll start our timer here to make sure we don't go over 30 seconds. You can see the speed of the engine's coming up. It's reached its peak. The temperature's way down. We'll bring in fuel, and we've got ignition. So that was only about 10 seconds until ignition. So you can see our start temperature is coming up. We have a limit here over 810 to 927 for 10 seconds. We're well below that. That was only about 700 degrees on the start. Oil pressure is coming up. We can release the starter now we've reached our minimum idle speed, and we're just waiting for the rotor to spool up. These oil pressure indications should extinguish. Those are for our transmission oil pressure indications. We've given everything a couple seconds to sort of settle out. The starter's cooled. We've reached over 40%. We can go ahead and come up here, turn on our generator on the right side. You can see now we're getting power off the right engine. The generator light's been extinguished. We can continue with our checks. So while we're waiting for the battery to recover, we can finish with our hydraulic checks. So essentially what we want to do is move the flight controls. We can look up here at our tip path plane. It's probably hard to see with the camera, but we can pitch forward and make sure the controls move around. And again, we don't want to move the controls too much and apply too much stress to the rotor head. You can see as I move the controls, there's a little bit of motion there, but the blades are still spinning at a low RPM. We're not going to put too much stress into the rotor head. Another reason why it's a good idea to do this now before we spool everything up. Come over to the side to make sure the roll is working. I come down and give the collective a little bump just to make sure that we've got good hydraulic pressure on the collective. Everything's looking good there. Come back down to our hydraulic switch one last time and reset it. You should see both the hydraulic pressure, the number 1 system, and the hide servo block light should be cleared. And those are extinguished. And we can go back and check our number 2 system, all the same checks. I'm sorry, check number 1. All the same checks, and that system is working. So the next thing we want to do is we're going to be starting our left engine. A couple things to think about. So now we're starting with more power since we have the right generator running. We're doing a cross-gen start. So that's going to change our starter limitations just slightly. Instead of a 30-second limitation, we're going to have a 20-second limitation. Again, it should be plenty of time. The other thing that can happen, however, is we are going to be applying a load to this right engine. And that load is going to be on that generator. And this engine is not anticipating that we're going to be applying that large load. The engine is really just trying to maintain this RPM. So suddenly if you put a load on it, it may not respond fast enough, and you may see that RPM get dragged down. You'll see this temperature start to come up as it throttles up, trying to maintain that RPM. And if the load was large enough, you could actually see an RPM decay in this engine. And if that happens, then you have to abort the start. So a couple things we can do to stack the cards in our favor. Number 1 is just wait and let the battery recover. Another thing that we can do is we can come up here and just make sure that we've got a good idle speed in this engine. So, you know, we've got 63%, just throttle it up a little bit. That should be plenty. You really only need about 58% as a minimum. So go up here and reach for the number 1 left side engine. We'll go ahead and hit the starter, start the timer. Again, it's plenty cool. Wait for the engine to achieve its maximum RPM. Looks like we're there at about 7 seconds. We'll bring in the fuel. That's ignition. We'll get that torque split. We can silence that. Looks like that was a nice cool start, about 700 degrees. And we'll wait for minimum RPM and then release the starter. And again, we'll just give everything a second to sort of settle out. Let that starter cool a little bit. And then we'll come up here. We'll engage that starter, and we can go ahead through all the other electronics that we still have on here, the artificial horizon, inverter and everything. The only thing that again, we still have this military helicopter, this vertical gyro is going to take just a moment to spool up. We can get the artificial horizon lined up. And normally, if this was the first flight of the day, what we would want is we would want to wait for these temperatures all to rise to an acceptable level. We really don't want to put a lot of RPM in everything while it's still warming up. We just stopped here temporarily for fuel. Everything's already got a lot of temperature in it, so we should essentially be ready for flight. So the final step is going to be raising our RPM into the flight RPM window, and you can see the vertical gyros aligned. So we'll come up here into our throttles, bring these all the way forward to the flight gate. We don't want to do it too quickly. So as we're throttling up the helicopter, we are putting torque into the system. And we're on the ground. There's no snow or water or ice or anything. So we shouldn't have anything to contend with there. If we were in a situation where we had some snow or ice on the ground, the helicopter could spin, or if we were on a dolly and we were putting too much torque into it, it's possible that the helicopter could spin. So we don't have a lot of risk of that today, but still we don't want to put a lot of stress onto the helicopter, so we will throttle it up fairly gently. And then we were talking earlier about this RPM indication system. So when you get the RPM up into this lower bound, it reaches a point where we'll start providing a low and a high RPM warning system. So this is our flight window, and when you're below the flight window, it's going to give you a low RPM warning, and when you're above, it's going to give you high RPM warning. And obviously the system does not provide any warning here at idle, because it's smart enough to understand that we're probably not trying to fly at this low RPM. And that RPM cannot be silenced. So the torque split RPM warning can be silenced. This low rotor RPM is not possible to silence it. So we'll go ahead and start accelerating the system. You can see that the torques are coming up, and we'll start to get this indication from the RPM system, and that will extinguish once we reach our flight idle. There we go. So we've reached our flight idle. You can see the system is a little bit low, and we're getting a little bit of this RPM warning. So we've got a couple solutions to solve that. We do have this control on the collective. We can bump the throttle up a little bit. Also, if we raise the collective, as we raise power in the helicopter, it's going to throttle up the engine such to bring it up to 100%. So it's just getting everything all set up to get ready to go fly. Now that we've got everything ready to go fly, we can give everything one final check. Temperatures, pressures across the board are all looking good. Again, it's very unlikely that we're going to exceed our torque or our NG, so we're pretty much going to be watching our TOT. And the one final thing is you'll see that when we get to flight power, we are going to want to match our torque, because this is the primary determinant of how much power is going into the system. And you can see right now the engines are putting out different amounts of power. Ideally, this would be balanced the whole way through. So you can see there's this control I have on the collective where I can put in a little bit more power in the right engine, and that brings those torques together. Unfortunately, this helicopter, it's new to our fleet. We haven't gone through and rigged it, but what happens is that as you throttle up each engine, they may throttle up differently. So now that I've matched them and we start bringing the power in, you're going to see them split the other way. So you typically have those balanced for flight conditions. So we'll go ahead and start bringing in the power. You can see our RPM is coming up. We're matching those torques. And watching the TOTs, we've got up to 810 degrees TOT for takeoff up to 5 minutes. It looks like today, even though we're heavy rolling, going to use about 720 degrees on the takeoff. Now we're ready to go. Well, that's going to do it for this episode. If you'd like to learn more, give us a call or a click. We'd be happy to help you out. Appreciate you watching, and we'll see you next time.